My name is Karou. I am PhD student at Polytechnic Montreal at LAMA-WeST lab. And we're also affiliated with MILA, that is the Quebec Artificial Intelligence Institute. So today I will be presenting how recent paper that is titled as Enhancing Frame Detection with Retrieval-Augmented Generation. So the talk going to be divided into 5 parts. The first one is the introduction. The second is the methodology. The third is the results. Fourth is the limitation, and the final and fifth one is the conclusion. Let's now see for the introduction. So we have these following problem statement. Recent LLMs, despite their impressive capacities, are sensitive to input prompt phrasing or lexical variation. If you have used any of the Gen AI LLMs, you probably have noticed that the way the answer you get depends on the way you phrase the question. And this problem is known as lexical variation and is active domain of research. So how way to solve this problem, what we propose as a solution to this problem is to convert all the lexical variation of a prompt or task description or question you may get into a unified structural representation. And how hypothesis is that a frame-based representation might be an effective solution to this problem. So, because talking about frame-based representation, a question you could ask is, what is the frame? And here we go. A frame is just a conceptual structure that describes a particular type of situation or event. That could be someone who is buying something, traveling, or communicating with someone else, or just doing an operation or commercial operation. And for every frame, we have the following items. We have the frame label that represents its name. We have the frame description that provide a comprehensive explanation of its semantic. We have the list of frame elements that are also a component of the frame, and they give additional details about the frame, like the contextual or relational information about the frame. And finally, we have the list of lexical units that consists of lemma pairs with their part of speech. So the task description, because we need a frame from a input text, we need to detect the frame. And so what is the description of the task? So, well, the task is just identifying the correct frame evoked in a given text or prompt or any task description using the target. The target are just part of the input text that we have to focus on so that we can accurately detect the frame. As illustration, we can have the following question: where did she buy the book? This is the input text. And in the data set, let's say this word buy is given as being the target. Using this target, we can perfectly detect the frame that is commercial buy. And we can go further, not just detecting the frame, but doing a mapping between the frame elements of the frame with the corresponding argument in the input text. So the buyer is going to be she, the good is the book, the place is not given, and the seller is not given. So these elements are the frame element, then they can be linked to element from the input text. So this is the fine-grained structural representation based on frame we get from the input text. So even without seeing the question, this initial text, we can know what was the text about, because we have that information here. We know that the buyer is she, the good is book, but we don't have the place. And exactly that is the question, what the question is looking for. So the following are our research questions. The first one is, does an integration of a RAG model enhance the frame detection? Second is, how can frame be accurately detected from a raw text without explicit target? From the previous example, I said that the target was by, and that helped us to detect the frame. And how, second research question, we want to do such task without having such information that is the target. And the final third research question is, what constitutes an optimal representation of a frame? So let's see now what have been done in the state of the art before presenting our methodology. In the state of the art, we have two main families of method. The third one is the generative or sec-to-sec approaches. They treat the task as a detection, like a generation from one sequence to another sequence, and they leverage large-scale pre-training, but they rely on the explicit target, as the example I saw in the previous slide. The second way is the representation learning. They map the context, the target, and the frame into a shared embedding space. And for that, we can use a graph-based neural network, like in this approach, KGFI, or just the constructive, as in the previous state of the art, that is COFT. Basically, what they do is to make sure that the representation of the frame and its target have similar representation in terms of embedding to the frame that is correspond, so that when we do the cosine similarity between the embedding of the text and its target and the frame, we have the highest value. And that was their way to detect a frame from the text. And in all these methods on the state of the art, the task description is given a sentence and the target, they have to detect a frame. And the major limitation in such approach is that getting such target is not easy at all. If you have to annotate every text by giving such information, saying that this position is what we have to look for to take the frame, that's too expensive to get. Let's now see how methodologies that try to solve that problem. So we want to detect a frame without having to get such additional information. So how task description is as follows. Given just input text, we generate all relevant frames that are evoked in it, and without having the target token. So we have to adapt to the original dataset by grouping the frame by sentence, so that for each unique sentence, we have a list of frames that can be evoked. So for example, after transformation of the dataset, as we describe how task, what we'll have as input is just sentence like this. I was sad when I couldn't go to the snack bar to buy soda, and the output will be just the list of frame elements. So you can see that we don't have information about the target. And that is why the task is much more challenging than what have been done in the previous state of the art. Let's now see the overview of how architecture that is called RCIF, retrieve candidate and identify frames. And just from its name, you can see that there is two components, the retrieval of candidate and then the identification of frame, the final frame that are considered as the good one. So frame embedding are generated using an embedding model. We have an embedding model we use to generate the representation, the vector embedding of the frame after representing it. And that vector is stored in the vector database. So in the second part, given an input text, all we need to do is to do a similarity search to get the most similar vector that are the frames that have been stored in the vector database. And finally, we have a fine-tuned LLM that will filter out some bad candidate and just keep the good one. So that is what we have in this figure. We have the FrameNet data set, and we have a list of frame in it. Every frame can be represented using whether the combination of each component. That could be the label, the frame definition, the list of frame element, or list of lexical units. And after getting the representation of a frame, we use an embedding model to get its embedding. You store it in the vector database, and we do the same thing for every frame we have in the FrameNet dataset. So now, when we have a new text, all we need to do is similarity search. That's just cautioning similarity between the embedding we get from the input text using the embedding model and what have been stored. And that way, the output will be the list of top K candidate. That can be noisy, but we have these LLM that have been fine-tuned to eliminate the bad candidate and just keep the good one. And finally output the list of what we consider as being the frame evoked in the input text here. In terms of dataset, we have used the two dataset FrameNet, the two version of FrameNet, 1.5 and the 1.7, and this they will show the distribution of data across different split. So the train, the depth, and the test validation. We also have after transformation of the dataset by grouping frame by sentence. This is what we have for every split. We have the maximum, the minimum, and the average number of frame we can have for a sentence. And we can see that the maximum 25, but on average we just have 5 frames per sentence. There are additional technical details about the fine-tuning of the model. So now I said that what we need to do first is to represent a frame before using an embedding model to get each vector embedding. And there is different way to represent a frame because we have different components of the frame. We can have the label, we can have the description, the list of lexical unit, and the list of frame elements. That is why we have tested these 3 options for the representation. The first one is just the label of the frame followed by its textual description. The second one, add the list of lexical units. And the third, add to the second the list of frame elements we have here. So as previously said in the overview of the model, of the architecture, what we do is the embedding model of all the frame are obtained using the English version of BGE. That is the embedding model we use to get the embedding. So once the frame elements are stored in the vector database, we perform similarity search when we have a new input text. And that way we retrieve a list of maximum 24 candidates for every input text. And the reason why we use the maximum is to maximize the recall so that the fine-tuned model will be able to eliminate a bad candidate. But it's much more, because it's much more easier to eliminate a candidate than having to pull out a candidate that have not been proposed. That is why we go with the maximum number of candidates in the retrieval part. And talking about retrieving list of candidates, the reason why we did that is we would like to reduce the complexity of the task, because we could just provide all the list of frame to the LLM and ask it to just find a good one, but it would be really complex. And this graph shows the complexity without filtering in this one. And this is the complexity when we do a filtering of the number of candidates. And we see that we can reduce the complexity by just retrieving a list of candidates instead of providing all the list of possible frames. For the final component, the second component, that is the frame detection, where we use the LLM to filter out a list of candidates. Here is the prompt we use to fine-tune the model. We have the instruction where we describe the task, and we emphasize what we expect as being the output. We give the input and the output. This is the information, the kind of prompt we use to fine-tune the model. Let's now see the results. So here are the metrics we use for the results. We have the precision, the recall for the candidate retrieval part, and for the second stage, that is frame detection, we have also the accuracy. We go further also by computing these metrics that are recalled at K being 1, 3, or 5. So for the candidate retrieval part, here is the results. And we can see this slide shows the insight from this table, so it's much more easier to go this slide and maybe come back. So the representation 2 and 3 yield on average the highest recall. As you can see, the 2 and 3 on average have 84, 85. So they are the best representation, the representation 2 and 3. All precision value remain low, yeah, of the retrieval because we retrieve the maximum instead of just the average. On average, we just have 5 frames, while during the retrieval, we retrieve the maximum that is 24. That is the reason why the precision is low. You want it to maximize the recall. Our hypothesis is that such broad candidate sets encourage the model during fine-tuning to rely less on parametric memory and more on generalization that enhance its robustness. And for the frame detection part, here is the result compared to what we have in the state of the art. And we have two experiments. First of all, when we give the model the list of candidates and ask it to just output the list of valid candidate, we sometimes on the first experiment, we give the information about the number of exact candidates it have to retrieve. That is what we have in the first part. And the second part is when we don't provide such information, just letting the model figure out the number of candidates it has to keep as being the final one. And the insight from this table is what we have in this slide. In the first dataset, FrameNet 1.5, we have slightly lower exact match accuracy, but slightly better than previous state of the art for both precision and recall. And as a reminder, we don't even use the target token. While on the state of the art, the previous state of the art, they use the target. And that is what you see here. They have better accuracy, just 1 point of difference, but we have better precision and recall in the first data set. In the second data set, we have highest recall. We have plus 10 point over the previous, that is COFT, as you can see here. The best performance in this data set was 87, while how is 97. So why how approach work? The two things are that with the retrieval, we trim the search space. So instead of providing the list of 1,000 candidate frame, we just retrieve 24, and that reduces the complexity of the task. The second is that the LLM that used to filter out the list of candidates keeps the true one, and that is the reason why the precision jumped from 5 to 92. So the LLM was able to keep the good candidate and eliminate the bad one. And in comparison between the two data sets, 1.5, FrameNet 1.5 and 1.7, we can see that the additional 26% we have in FrameNet 1.7 boosted the generalization, because that is where we have better results. So the additional data we have in FrameNet 1.7 was useful to boost the performance. And that is important to emphasize that we don't have the target span. We don't have the target. And comparing these two results for the different data set, we can see that providing the information about the exact number of frame the model has to detect was not that useful, because the results were not different, were not really different. So the model didn't even need such information. It will just figure it out by itself. And here are the results when we just use the training, the additional training data, that is the exemplar. And from the result, we see that training with exemplar data hurt performance, and the same was observed by previous work, Channing. So the reason why is in exemplar, a sentence typically has only one frame, and such data is not suitable for training. The reason why is there's exemplar are synthetic data. So not that as good quality as what we have in the train, validation, and test split. And so there's exemplar data are not really useful. And in terms of recall at k, we can see from this table that for k equal to 3, we have reached between 94 and 95% of recall. And when k equal to 5, we're in the range of 95 and 96. So how approach is nearly identical. We have nearly identical gain on both data sets. And how approach generalized despite schema change and large label set. Let's now see the limitation of the work. The first one is the task description is a bit different because we don't have the target token. So compared to the state of the art, some might think that that's not a really valid comparison. But what we could say is how approach is much more difficult because we get rid of that. We got rid of such information and just detect the frame from the input text. And that align more with the reality. In the reality, we just have text. We don't have information saying that this part is what we have to focus on to get the frame. The second one is the list of frame is not associated to values span in the input text, but rather represent a backup frame. As you can see from input text, we just provide as input the list of frame without linking the frame and the target of or any part of the text that have been used to detect such frame. We just have a backup frame without linking element of the input text with these frames. And you might have noticed that the proof in the very first slide in my presentation, I show you a fine-grained representation where every frame element is linked to part of the input text it aligned with. But we didn't do that in our work. All we did is from input text, we give as output a list of frame. So we need to do that in our future work. And to do that, we have to get much more big data set annotated. So in conclusion, we introduced the RCIF, the retrieve candidate and identify frames. That is the first rack-based pipeline for frame detection. It's span-free, that is really important. We don't use any target to detect the frame. We just have to give as input to the model the input text, and it will figure out by itself the list of frames. It's pretty simple. We just have two components. We have the candidate retriever that trim the search space and reduce complexity. And the second component is the fine-tuned LLM that selects the correct frames. In terms of performance, we got the new state-of-the-art in terms of precision and recall on FrameNet 1.5 and 1.7. And we have plus time recall over pure work on FrameNet 1.7. Practical impact is that it's more suited for real-world application where only the sentence is available. We don't have the target. And for future work, what we used to do is to use such representation to solve the lexical variation I introduced in the first slide. And we already have a preprint article that do such thing. We use such structural representation to solve the problem of generalization over template-free question. The task was to generate Sparkle query from natural language question. And the one problem was that when we use questions that are not template-based, the model was not able to generalize. And through this structured representation, we were able to improve the generalization capability of the model. So the work is called the phrase. You can check it out if you want. So as acknowledgement, we would like to thank to Unstructured and Ivado. Also, in terms of computational research, we use the cluster of Compute Canada, also known as Calcul Quebec. So thank you. That is all for the